So I just want to put a little bit of context on the statistical mechanical calculation we did and the thing that, in fact, it's just one example of. So this is what you might call classical thermodynamics. We have, for instance, the ideal gas law. And the idea of classical thermodynamics is we have a collection of thermodynamic variables. And they describe everything there is to know about the system. So for instance, if you know the complete collection of P, V, N, little n for mole number or big N for particle number, and T, and then later we'll throw in entropy, you know everything there is to know about the system. So that's thermodynamics as an intellectual pursuit in and of itself. A really important set of questions, and one that we took a little bit of a dive into, is, okay, but let's say that you know this stuff. What can you tell me about, for instance, mechanical properties of the gas? And that's what kinetic theory does in a sense. So we came up with a calculation, we made some assumptions. So for instance, these things were non-interacting point particles. And we'll revisit that assumption. And we asked, well, how frequently would they bounce off the walls of this box if they had some particular speed? And what would that tell us about the pressure? Because every time they bounce off the wall of the box, there's some momentum change. And what we got is this result, which does let you relate the pressure. So this is P for pressure, not momentum. The pressure to some properties of the gas itself, namely its mass and velocity squared. And then what we realized, and this is like really neat, is if you put the P and the V on the same side and you know that this is equal to nkt, so what you have is a relationship in between temperature and this thing VRMS. And that is actually a really important point because it tells us something that, to be honest, we all kind of grow up knowing at this point, really what temperature is. So you can associate temperature up to some constant gu with the kinetic energy of the particles within the gas. So the average kinetic energy in the root mean square just basically means fancy average is equal to 3/2 kT. So this again, the 3/2 part at least, or the 3 part, is for non-interacting point particles. We'll talk about what happens when you make them not point particles. We won't talk too much about interacting outside of the context of this video, and just qualitatively at that. So this is really great, is our one trip into statistical mechanics returned this wonderful result of like literally what is temperature. It's average translational kinetic energy. So now what you can see when you look at this is not only do we have, for instance, the ideal gas laws and the relationship in between volume and temperature, is I can ask what the average, so that particular type of average, VRMS, at 200 degrees Kelvin is. And I can ask, for instance, what VRMS is at 500 degrees Kelvin. But there's more. So beyond what we'll talk about in lecture and make you guys do kind of real-time calculations about, is that you can actually go farther, and VRMS really just tells you, in some sense, the average of this whole distribution. So what the distribution is it tells you not just the average, but how many particles you have at every particular speed. So cut off on the horizontal axis, this might be 100 meters per second, 200 meters per second, ... And the whole distribution, namely this is what's called the Maxwell-Boltzmann distribution. And this works for so-called classical non-interacting particles, is this basically tells you the fraction at any particular velocity. So what I could do is I could look at the area under the curve in between here, so this would be like 400 meters per second and 500 meters per second. And basically the bigger the area, the more particles I would expect to see there. So basically this is a histogram. And this is literally everything that you could possibly know. Imagine knowing the details of a gas that has, a mole of atoms. So this is really like the full results of StatMech, and we won't get there, but I want you guys to know it exists. So this is what the Maxwell-Boltzmann distribution looks like for a variety of temperatures. If the temperature gets really low, it would be really spiky and die really quickly. And as the temperatures get higher and higher, basically the particles get all smushed out. And if you really get into this, now not only do you know classical thermo, but you also can make some statistical statements about where the particles are, so the fraction of particles at, in between two particular speeds. And that would get more and more smushed out as you get warmer and warmer. Okay? So there's another set of questions you can ask, and you can give it the full treatment of classical and StatMech, or classical thermo and StatMech. So one question that comes up, and probably you've thought about this a little bit, or you just trust physicists too much, is that when you look at the ideal gas law, it tells you two things, and it's witnessed by just looking here, for instance. It tells you that when t equals 0, V is 0, and P is 0. And I have trouble believing that that actually describes a real gas, because if I have, even a classical gas, think about them as billiard balls. If I get them really cold, yeah, they're not bouncing around, but yeah, they take up volume. And secondly, I know that atoms interact with each other. So if particles didn't interact with each other, there would be no such thing as chemistry. Chemistry is the science of particles, molecules interacting with each other, atoms and molecules. So I know that this isn't quite a good description and complete description. It's pretty good for a large variety of temperatures, but obviously at some point, we're going to run into a wall. So the types of things you can do is you can actually include, so for instance, finite volume effects like this, and you can include interaction effects. So one way of doing that completely classically, where basically you change P and you change V, you would get something like the van der Waals equation of state. It would just be PV equals NKT, but P is different and V is different. So you're correcting for the fact that the particles take up some volume and the particles pull on each other. So you might see that. It's basically including a little bit of this stuff, what you would call empirically. What I really want to point you guys towards, because this is pretty neat and this is pretty new, is what happens when you get really, really, really cold. And at this point, you have to give up on describing things as classical particles, because the laws of quantum mechanics, which actually always describe particles, are more relevant. So particles are not finite volume, hard sphere billiard balls. They're quantum mechanical. They got weird wave function stuff going on. And you can basically parallel this entire discussion. You just can't use the Maxwell-Boltzmann distribution. So you would use, for 50% of the types of quantum particles, like photons in a laser, you can stack as many of them as you'd like. Turns out for 50% of the things on the periodic table of element, that's also relevant. So these are what are called bosons. And they have their personal distribution called the Bose-Einstein Distribution. And they act funny. So this is superfluid helium. It's got no viscosity, so it's crawling up the side of the wall, going around the side of this glass container, and then dripping on the ground, because it knows that this is like the lowest energy state and it wants to be there. So on this picture, what there are electrons pairing together to make so-called superconducting currents. So these superconducting currents basically refuse to have the magnetic fields that they create be changed. So this person is picking up, so that's just like a normal rare earth magnet, and the top part is the superconducting magnet. It does whatever it needs to do to keep its magnetic field, including levitate upside down in the air. And the white frost you see on it is it's so cold, because all this stuff happens down here, that it's condensing and solidifying water vapor. So that's just ice crystals on it. So this is happening at about like 2.7 degrees Kelvin, so 2 or 3 degrees above absolute zero, so that's pretty cold. And this is happening actually a bit warmer at like maybe 80 degrees Kelvin. So superconductivity can actually happen at pretty quote-unquote high temperatures. But basically this is stuff that you can still describe with thermodynamics. You just can't use the results that we used because these are not classical particles.